James Abello. I first met at the Institute for Pure and Applied Math at UCLA during an Institute for Advanced Topics in Digital Humanities, where we were bringing network models to the humanities back in 2009. So I'm deeply pleased to be able to welcome Professor Dr. James Abello and Haoyang Zhang, who I've been working with now also for close to 4 years on using network methods to understand complex phenomena such as the rise of anti-democratic storytelling on social media. So without further ado, the floor is yours.
Thank you so much. So I'm here ready to learn. I am very ignorant about many of the things that you know. So the goal for me this week is to learn. Maybe I should tell you the few little things that I know. And maybe that could start a conversation between what you do and the little that I know. What is the setting here? We have this title there, Graph Cities. And can anybody tell me, what that title says? It says Graph Cities. Can anybody tell me what that? You are not supposed to answer. Okay, let's show a picture. So there is, no, there is. That's a graph. So what is it? That is a graph, and I'm assuming that all of us know that graphs are dots and connections. This is a graph that has 1.8 billion connections. And this has been a major achievement for our group. I used to work in Berkeley labs many years ago, and the data there were phone calls. So each point was a telephone number, and you will call another telephone number. That would be a connection. And every day we were processing. This was like before the internet. I am that old. It was before the internet. We were processing daily what is called the phone call graph. And then the question is, how you process that? What kind of questions you can ask? And I remember very well my boss, in one of our presentations of the group, said, show us a picture. I said, what? This has 300 million nodes, billions of connections. In a week, at that time, we have something like 4 or 5 billion phone calls. I said, no way. So this is the culmination. Unfortunately, he died. So if you couldn't see this, this is the culmination of, we can show now pictures of networks with billions of connections. Should it be called a city? You judge. But you see these structures that look like buildings. And you see also some green areas. Those green areas are like little parks where the buildings around those little areas are small buildings, and the center of the city has the big buildings. We can generate this in the order of 40 minutes in a normal laptop. And the rendering of this, the visuals, take about 9 seconds. Okay, so the question is, what are these things? So that's the next question, is how did we create this? And I was very excited this morning when you guys were describing what you were doing, I said, oh, maybe I can tell these people something that would be helpful. In almost all the comments that you made this morning, I had this map in my head telling me, wow, this is going to be a nice way to, we're going to be able to put together these two different languages. The one that you speak and the ones that I speak. I think we are going to be able to put this together. And there is one idea, well, maybe two. Let's say one big one. This idea of waves. And we are creating a concept of waves or any network, big or small, any network can be described as a collection of waves. And I'm going to, in the next 5-7 minutes, to share with you how is that possible, both computational and visual. And if we agree on waves and what they are, then you will be able to generate this picture. Well, but the picture is a picture. So it's a static picture? No, these pictures are dynamic. You can go inside the buildings, and we are going to show you something like that. So everything is based on one idea, waves. And the second idea is sequence of waves. And then you can start making the mapping in your head about what you do. You have a conversation, you have a movie, you have a book. What are the sequence of waves in that narrative? Well, now I use the word narrative. Well, you see, that's outside my field, that's you guys. But I think we can put it together. Okay, so let's go into a couple of technical things, which are very scary, but all this is symbols. See, we in computer science and mathematics, we put the symbols and they look fancy. I tell you what this whole thing is in the next minute. Think of your favorite network, phone calls, or the internet. Each point is a web page, and the connections have the links to the web pages. So fix one of those in your head. Now, each of these networks, every point in the network has a certain number of connections. That's called the degree. Okay, what you do is identify all those points that have the minimum degree. That's very simple. When you identify all those points that have minimum degree, let's say this guy here, I'm going to look at the topology as you are sitting. He is close to these two, and he has minimum degree 2, let's say. I say, think, go home. I remove, I will show him. I remove him from the network, and now I repeat. Now, when I remove him, he had degree before 5, and when I remove him, now his degree goes down, right? So now I repeat. And what do you do next? You repeat. And what do you do next? You repeat. Until when? How are you going to be putting these guys on minimum degree? You are also minimum degree. Okay. You are also minimum degree. How far? I'm going to repeat this process. There is only one parameter. That parameter is what is the value of the minimum degree. Suppose that the minimum degree is 10. That's your parameter. Minimum degree 10. Everybody less than equal to 10. Go home. Everybody go home. At some point, what's going to happen? Maybe everyone went home. If that happens, you guys are a bounded small network. With minimum degree 10, I can send you all of you home. That's the parameter of your little network. So far, you got? That's called a fixed point. You just say, hey, oh, wait a minute. But if you are doing minimum degree 10, minimum degree 10, minimum degree 10, minimum degree 10, and at some point, it could happen that there is no minimum degree 10 anymore. The network is more complex than just this minimum degree 10. And at some point, you say, oh, I'm working with minimum degree 10. Is there anybody minimum degree 10 here? Nobody. At that point, you say, oh, yeah. Are you fooling me or what? What is the minimum degree now? Oh, 15. Now you say, that's my new parameter. I'm going to take that 15. Minimum degree 15, minimum degree 15, minimum degree 15, minimum degree 15, minimum degree 15. And you're going to have another piece of the whole network detected with minimum degree 15. No more minimum degree 15, now minimum degree 20. Repeat. So you're finding these groups in your network with one parameter every time. Okay? Is that clear? Now I want a picture. I take the first group with minimum degree, I don't know what I say, 5. I said, you guys are on the first floor. The next group, minimum degree 15. You guys on top of this, the next floor. The next group, minimum degree, go on top, go on top, go on top. Go on. That forms a building. So visually, we are going to map this group and the next group into a frustum. So this and another this and all the connections. That's the floor of the building. The next group, stack it up as another floor of the building, etc. And that's a kind of picture that you have here. This is completely clear? Semi-clear? Okay. You can do this for any network independent of size. So for any network, you can have your city. And if you have data and you want to create your city, we give you a link and you can create it and take the city home. Complete your city in the jacket. That's it. Waves. Next stop, waves. Each of these groups, when I delete 15 on minimum degree, think of it as a wave. Why? This is not the only one with minimum degree 2. You also have minimum degree 2. And she also has minimum degree 2. I can take all of them simultaneously, remove them, and repeat it. You can characterize this graph theoretically as a sequence of waves. And you can do that for narratives, for social media posts, and almost anything you can think of, as long as you can define what are your entities and what are your connections in your network. Okay, so maybe they show the little video. That's inside the building. Each ball is a little cluster. You can expand that ball. Inside looks like that. That is layers. Movies. Every point represents a movie. And two movies are connected depending on the reviews of the movie. You have the movie network.
Yep, I'm also not.
So for example, here you see Chinese Odyssey. Saigon. Might be how it is. But he finds these clusters. Even though this has no knowledge about words, absolutely no knowledge about it. It's just reading those labels at the end of the process. And happens to be that they are very related. So the semantics pops up without you looking for. Let's look at this fragments thing. So okay. The previous one. So this business of fixed points, this business of taking something, remove it down, repeat, happens to be that these things appear very well, everywhere. This, for example, is an example of a fixed point or something called a random geometric graph. The minimum degree here, I think, is 5 or 6, something like that. And these things appear all over the place. So the question is, are these very special theoretical constructions in mathematics, computer science? Theorem. Any network, any, can be decomposed into a collection of fixed points. No matter what it is, the internet, the web, phone calls, narratives, and if you define a graph for the narratives, movies, any such network can be decomposed as a union of fixed points. And each fixed point has a parameter. That's exactly what that is. Now, all this looks fancy, but there is one computational thing that we discovered. One thing. No more, one thing. And this you are going to fully understand in the next 30 seconds. Take a collection of points in your network, whatever that it represents. Look at all the connections that touch those points. He's interested in elephants, you are interested in mines, you are interested in something else. Now in your connections, look at everything that touches this point. Every connection that touches this point. Every connection that touches this point. Take all those connections together. That's called a fragment. So mathematically speaking, it's very simple. You start with the set and look at all the connections that touch these guys. And you have to be careful because he is minimum degree 2, but if she was very close, maybe they too are also connected. That's the only detail. Definition. Give me any collection of points in your data. Look at all the connections touching those points. That's called a fragment. Theorem. any network, independent of size, is a stacking of fragments. So some networks may have 100,000 fragments, some others may have 20 fragments. This business of fragments, semantically, we have found correspond to the notion of waves. The trenders, the social influencer. You take some guys and you are going to look at what is that we are talking about, and you iterate this process and give you the weight generated by this particular collection of anthropons in your discussion. The moral of the story here is that we don't have any preconceived notion of what is propagation. It depends on your network. The network connectivity defines the propagation. Okay. Now, so these are these pictures. I think we can. This is pure graph theory. Now let's go to the next subject matter. No, over there. Go. Yeah. So you see something very complicated like this now becomes a linear structure like that in the visual representation. So you computing your data, all these fixed points, and each fixed point, which is a graph, this is what the computation is doing, has a corresponding building that the visual representation. Now all these things are laid out circularly, and then on top of that, you have the corresponding building that gives you, this is a little graph city. The same thing can be done at a scale. Okay. Maybe we go to the next interesting idea, I think, for this group. Each of these pieces has its own set of influences. Influences are these beginning points, and they generate the waves. And over there is another group. It has its own parameter, it has its own set of influences. And over there is another group, it has its own set of influences. How do you glue them together? You can have bit being a serious influencer in this subgraph. But Pitt, which has been a great person, great researcher, he may also play some sports. So he has his own networks with the sports community. He could be also an influencer there. So the roles that we play depend on the network that we are in. But in real life, we don't have only one network. We have a family network, we have a professional network, we have a sports network, we have a drinking buddies network, etc., etc., etc. The difference in this world is that a point in a data set, whatever it is, an entity in a data set, does not have only one role. And this is what this world does. Team, art visual, the Scandinavian department, family, motorcycle, you have the problem of motorcycles now, but team is a multifaceted man. This is what this world does. It splits team into these different roles. Oh, but in real life, his network of motorcycle people could be quite different to the network of academicians. But in the data, he is playing two roles, so we need to be able to explain how these two roles get glued together. So the mathematics of this is, I think the matrix. The mathematics of this is a matrix formulation. Each of these rows corresponds to a fixed point, which is one of these groups. And over there on the top, what you have is the members of that group. Happens to be that each of these guys, let's say, for example, vertex 34. Vertex 34 has 13 connections on one fixed point A and has one connection in fixed point 1. The number of connections of 34 is really 14 that are split into one group of 13 and one group of 1. The number of connections of, let's say 39, that's interesting. 39 is a very active guy. That's like a team. It's kind of a team target leading guy. He has 6 connections in one group, 6.5. 4 connections in another one. 3 connections in another. Team Tangerini's connections are 6, 10 plus 3 is 12. His network is really splitting him into 3. This matrix is a small matrix. In general, you have these gigantic monsters. They are split into pieces. Each piece may be big, but the number of pieces is not too big. So, that's lovely in computer science. In computer science, when you have something big, what do? Divide it, split it into pieces. So what this board does is it takes a huge, gigantic thing, break it into pieces, and on each piece, apply whatever you like. And then at the end, put the semantics to that. So computationally, this is the nice thing about this. Big things can be decomposed. I think I don't want to. Yeah, maybe the show it's all about eccentric representation. The next one, this is a very nice idea. Maybe it's also useful in your work. This idea of something called barycentric coordinates. Remember, team has been split into several pieces. So you can represent this by drawing a circle like this, and now each point is split somehow around, depending on the number of fixed points that you have. The coordinates of that point is the split. Team Tangerini is split into something for SP1, something for SP2, something for SP3. So the life of Team Tangerini is depending on these connections to here, to here, to here, to there. And that can be mathematically represented as something called barycentric coordinate. Oh yeah, that's a very tiny example. What happens if we have something big? So let's show the COVID. So you can apply this, for example, to the COVID social media. This is a small example, but it conveys to you that now when you split this into pieces, in each piece you have certain groups, you can use clustering, and now you can look at what each group means. And let's look at the summary. In social media, this particular cluster happens to correspond to emergency and curiosity, and you can read that if you want. Let's look at another one. There is another group that corresponds to panic and polarization in social media. See some sort of doubt and global framing, conspiracy theories stuff. Bureaucracy, censorship, and lingering skepticism. The system knows nothing, no knowledge at all. You just take points, connections, split it, and do some local clustering, and you get this. Okay, now let's summarize the whole infrastructure. So on the top we have data, whatever level you have. Then in the middle you have a matrix that represents the interactions between the different fixed points. Then you can apply different techniques to find clusters. And if you are very curious, and you got it hard, and you really would like to get a view of something like 100 million entities, and you would like to see the waves of this 100 million in some kind of picture. And I don't think I have the time to go over the details, but this is the kind of picture. That Graph City has some picture that is like a cone with some rays and has colors. This is a way to summarize 100 million things. Using what? Barycentric coordinates in 3D. So let's go now with the, yeah. So let's, and this is what we did with Team Tangerlini. When they saw the name Team Tangerlini, they gave us a prize. That was in Paris. No, Dijon. And then we applied this to social media posts. It's another technique. It's something called max flow win code. You don't have to understand what that means, because at the end of the day, this is what you need to understand. What do we do with social media posts? And that was something that Tim did. I did not touch that. Did you use some kind of modeling BERT or something? And he took the social media posts and he transformed this into collections of triples. Three things. And the thing in the middle is a connection between the two. That's the data model. And as usual, Tim picks up the phone, or we are in the chat and say, hey, I wanted to look at that data, but it looks like a headboard. That's how this work started. Because I love when Tim comes to me saying, we have a headboard, because we have been able to disentangle all these headboards. And some of them coming from folklore, by the way. I know you are aware of modern world between. Okay, so that's what we did. We take those triples define a network between these two cells, and the connection has a label. So we took that network, the whole of triples, and push the machinery, divide it into these pieces, divide it into these fixed points. And something very interesting is that you take these influencers, as I described before. He has certain triple, this influence. He has certain triple, this influence. And we look at these waves. What is it that is being passed to a different way? The label. So you can interpret these waves as passing labels. The labels that they have get passed to these guys. Now you guys here have these labels plus your own label. And how you pass it through? The next cell. So you are accumulating labels. These are the waves of the conversation. And then what we do is we apply, this is a theorem, a beautiful theorem, that where all these labels accumulate the most. There's a theorem that tells you it happens, something called mean God, but that's not important. But after that, to interpret that, we do exactly the barycentric coordinate that I showed you before. And then we have an interpretation. So let's look at the demo. So we apply this to
A Max Floman cut view of social media posts by James Abello, Dintanger Lini, and Haoyang Zhang. We treat social media posts as collections of entity, verb, entity triples, which form a graph. This graph is then partitioned into fixed points through an iterative edge-core decomposition process. For each fixed point, we apply local label propagation and iterative max flow min cut decomposition to extract summaries. These summaries are then displayed in a barycentric representation, showing how they are related. Let's begin with the highest fixed point in the parlor dataset. Fixed point representative context labels are placed in the periphery ordered by their ranks. Cuts are placed in the center of the circle according to their context labels. Hovering over a cut opens a local lens view of its local context. Biden, court, evidence is contextualized by Trump, people, party, vote, hinting evidence of a stolen election being used in the courts as a possible intervention. Moving right to the periphery, discussions are characterized by Republican, Trump, people, Washington, party, vote, Biden, ballot, evidence, court, truth, tongue. The second highest fixed point of the parlor dataset is more focused on aspects of fraud, the power and size of Trump's Patriot supporters indicated by intensifiers such as Milia, the role of actors such as Dominion and Democrats, broad groups such as leftists and communists, and the corrupt deep state efforts that characterize the response to the pandemic. The French Twitter fixed point 7 is focused on concerns about Islamization, the European Union, nationalization, and the business climate. The centered node discussion flow includes defeatism, medicine, and Moscow set in the context of patriotism and Lepinism, anchoring this discussion the challenges Europe confronted in the 2010s, and the rise of right nationalist ideologies such as those of Le Pen. We would like to extend our special thanks to our collaborators.
okay, so this gives you an idea. So this gives you an idea of how we can use graphs in different contexts. And here, Tim came. He said, I have an exquisite stuff. So exquisite. So he had these Danish recipes coming from a particular book. But this is airborne here, it's airborne. And I said, oh, really? Huh. When we apply the previous methods to this, and we discover a limitation of the modeling. The limitation of the modeling is that graphs actually look at only two things at a time. Two things at a time. Now there's something called hypergraphs, which is just a hyperword it's a collection of sets. So the data can be modeled as a collection of sets. Now you are lifting this to the hypergraph arena. And what does it mean, hypergraph arena? Don't think very hard. It's a whole bunch of sets. So if your data has that, now what do you do with a whole bunch of sets? When you have two sets, what is that you would like to do? The data set? Or maybe is this set a subset of the other? Or if they intersect, maybe there is something that is in this set, but not in this set, and something that is in this set, but not in this set. So when you have sets, these are the three things. So that's what we do. And we can generalize the methods that you saw to set systems or to hypergraphs. And we're going to show you what is coming out of that with an interface. This is work in progress. And that interface is not at this point for large data because Tim just gave me 800 recipes with 300 ingredients. And I need to please him. But the methods can be lifted. So we show you that. And that, here we are final.
Yeah, that'll be the end, I guess.
Okay. So set systems are collections of sets, and we can do some fancy description of that. That's not the point. Let's go to the interface. Okay, so here on the left-hand side, you have recipes. Each of those many things are recipes. And we connect two recipes if one is a subset of the other. That's that. But what is a recipe? A recipe is a set of ingredients. Of course, you are going to come to me, yeah, but you should be interested in how to cook it. Yes, future work. Right now, a recipe for us is just a set of ingredients. So these are the recipes, these are the set of ingredients. So Haoyang, what can we do with it?
So to disentangle this hairball, the first thing that we can do is, well, let's start with all the recipes that are minimal. That will be placed at the bottom layer. And from those minimal recipes, we can check what are the corresponding ingredients that are used in those minimal recipes. So we put those corresponding ingredients also to the right-hand side at the bottom.
So bottom line, these are precisely these H fragments. The same thing that we did before, but now with sets. These are the waves or the Danish recipes. These are the Danish recipes on the left-hand side. And these are the corresponding ingredients, and yes, and you can say, okay, fine, so what? This took us a lot of time. So let's show more.
So we find some interesting recipes.
Can you read them?
So here we listed 12 interesting recipes, including breaded pork, meatballs in brown sauce, spring vegetable soups, tarts with asparagus and shrimps, minced meat hash, chicken meat soup, fried pork fatty with beef sauce, rice a la parmande, pork chop cutlets, BUMF. I'm not sure how this was used in Danish. Rostos with hams and herring with ramna.
So I'm sure Tim recognized those 12 recipes.
Pretty much.
Okay, so these are, now we look at how these guys are related to each other by using interconnections based on subsets. And then you have these other guys that show up. So tell us something.
So we starting from those search recipes, we do the fragment iteratively until they become connected. In this subgraph, now we check what are the sources, what are the minimal recipes that I can use them to expand to those interested recipes that we are focusing on. In this case, we found grounded beef, shrimp, freezing ice, grounded butter, prepared milk, and hing egg. That means if you want to cook those recipes, well, you should better start preparing those minimal recipes. On the right-hand side, we have the corresponding ingredients that are used in those search recipe. And we also show that how those ingredients are connected to each other via the sharing of the superset of the recipes they participate in.
Okay, Haoyang, maybe we should ask them to give us, to close, maybe you guys can tell us, I don't know, 4 or 5 ingredients, because we can search this space, you can type some ingredients. So, think, not nice, right? Don't mention 4 ingredients.
Let's do cream.
Cream,
I guess we could do potatoes, yes.
So we want to use both cream and potato.
Cream, potatoes, and pork.
Cream potatoes is here.
Nice. How about just pork, butter, not like Denmark.
So butter.
Pork and butter.
Okay, okay. And we want butter. So all those pink recipes are recipes that are using pork and butter. And among them, if you want to cook them, you should better prepare brown butter and freezing ice.
and what about the right-hand side, what the heck is it?
Right-hand side is says that between the pork and the butter, if you want to connect them, what is the common ingredients that is used for both of them? This is the beef broth. So you can cook with the pork with beef broth, and you can also cook with brown butter with beef broth.
What is that CNN tape?
Yeah. So when you so it is showing that what is the last hovered ingredients if you hover on the right hand side, and what it can be used for cooking.
So when you hold the ingredients at breaking news CNN type tape. So the point about this is that I think that you can, for any set system you have, if you have well-defined entities, you can use this type of interface to search for whatever you want, any substrate, any substrate. And that is a major achievement. Why this can be done? Well, there is a little bit of combinatorics behind the scenes. Okay, with that, I would like to thank people with attention. If you have questions, this team is the man. Okay. Thank you so much.
I want to thank our speakers. This was fantastic. It's also great to see some work on Freuchen Jensen's COBO and some discoveries there. We're continuing to work on the flavor networks. And now we've got a pipeline that's churning through Norwegian, Swedish, and Danish historical cookbooks. We should have 100 of these for you to work with pretty soon. In the spirit of time, we're going to start the next talk in 10 minutes. There'd be enough time for like a question, and then we've got a deep dive with James and Haoyang. Where is that taking place?
Put me on the spot. Just
Yeah,
it'll be over at AI Futures Lab.
It'll be over,
I know exactly when.
We're building AI Futures Lab. I think later on tomorrow morning,
I
right?
think it's tomorrow.
Yeah.
Tomorrow morning, yes.
Yeah.
At 9:30.
9:30. And then of course they're here for the week, so another opportunity to speak with them. But if there's a burning question now, and in the meantime, you could also, if you want, you can also grab a water or something like that. We're going to start the next talk at 1:15 because we've only got this room until about 2:50 because we have to clean it up. Is that right?
Yeah.
Yes. But please, if there's a question.
So everything was so clear. Undelighted. Any comments?
Will there be a problem set?
Huh?
Is it going to be a problem set? Do they have to? Yeah. Okay. So